let's revise indices today. The rules of indices, or as they are sometimes called, the rules of exponents, are not new to you. So let's go over them very quickly. The first rule that you know is that when a times a to the power m is multiplied by a to the power n, you simply add the indices. The condition being that the bases are the same. An example of that is x to the 5 times x to the 7 is simply x to the 12. You add the indices. The other rule is quite similar, but when you divide two numbers, the same base, different indices, you simply subtract the indices. An example of this is 5 to the 9 divided by 5 to the 6 equals 5 to the 3, because this 3 is 9 minus 6. The third rule is when a number raised to a power is raised to yet another power, the two indices are multiplied. So a to the m to the power n is equal to a to the m n. An example of this is 2 to the power 3 all raised to the power 4 is equal to 2 to the 12. And the reason is this 2 to the 3 is basically 2 to the power 3. When it's raised to the power 4, it's multiplied by itself 4 times. And using the first rule, you add the indices. So 4 threes is 4 times 3, and that's 2 to the 12. A to the 0 is 1, as long as a is not equal to 0. And I want you to think about this condition, and let's discuss it tomorrow. Why is 0 to the 0 not equal to 1? We'll talk about that. However, why is a to the 0 equal to 1? You can think of a to the m divided by a to the m. It's a number divided by itself, and that equals 1. However, using the rule of indices in the case of division, this is equal to a to the m minus m, which is a to the 0. Therefore, a to the 0 is equal to 1. A to the negative m is equal to 1 over a to the m. So a negative in the index means 1 over. It does not mean that the number itself is negative. Now, why is this the case? Based on the previous result, this one can be thought of as a to the 0 divided by a to the m. And using the rule for division, this is a to the 0 minus m, which is a to the negative m. Therefore, a to the negative m equals 1 over m, and by a simple case of rearrangement, you can conclude that a to the m is also equal to 1 over a to the negative m. And this is something that we're going to use later when simplifying expressions. A to the 1 over m is equal to the nth root of a. So a fractional index means a root of some type. And we can demonstrate this by saying that a to the half, whatever that is, times a to the half is equal to a, because we're multiplying two numbers with the same base, so we add the indices, a to the half plus a half, and that's a to the 1, which is simply a. But what multiplied by itself equals a. You should know that the square root of a times the square root of a is equal to a. Therefore, a to the half is equal to the square root of a. And by the same token, a to the 1/3 is equal to the cube root of a, and so on. A to the power m over n can be considered as either the nth root of a to the m or the nth root of a all to the power m, and that's exactly the same thing. How come they are two different things? Well, it depends on how you look at this expression. You can either look at it as a to the m all to the power 1 over n, and using the rules of indices, you multiply the m times 1 over n, giving you m over n, and this results in this expression, the nth root of a to the n. Or you can think of the same expression as a to the 1 over n all to the power n, and obviously multiplication is commutative, so 1 over n times m is this power m over n, but this means that we're talking about the nth root of a raised to the power n, and they are both exactly the same thing. However, it is more common that we use this form. The index can be distributed over multiplication. So a squared times b all raised to the power 4 is simply a squared to the power 4 times b to the power 4, and this equals a to the 8 times b to the 4. However, I don't expect you to write this step. This is just a waste of time. And keep in mind that the power is distributed over multiplication and division, not addition and subtraction. This is a particularly nasty expansion. You have to multiply a squared plus b by itself 5 times. The power is not distributed over addition and subtraction. So this does not equal a to the 10 plus b to the 5. This is exactly the same as x plus y squared does not equal x squared plus y squared. Be careful. So, using the rules of indices, how can we use what we have just revised? Keep in mind that something like 2 to the negative 1 is simply equal to a half. Also, 5 to the negative 2 is equal to 1 over 5 squared, which is 1 over 25. So this leads us to a concept that is called scientific notation, or scientific form, or standard form, whereby we use the powers of 10 to express very large or very small numbers. So for example, 3 times 10 to the negative 4 is equal to 3 times 1 over 10 to the 4, which is equal to 0.0003. And very large numbers can also be expressed in the same way. For example, 5.9 times 10 to the 7 is simply 59 million. 5900 1 2 3 and another one. So this standard form is much better than writing so many zeros and not being able to count them. And using the rules of indices, we can do the operations such as 3 times 10 to the 9 times 2 times 10 to the negative 6. Now this is a very large number multiplied by a very small number. And this can be done by simply multiplying 3 times 2 giving 6, 10 to the 9 times 10 to the negative 6, you add the indices 9 minus 6, and that gives you 10 to the 3. Another application of the rules of indices is to simplify expressions and to express them without negative indices. For example, x squared y to the negative 3 divided by x to the negative 4 times y to the 7. How can we simplify this? This can be done in one of two ways. Let's start by the first, saying that we are dividing x squared divided by x to the negative 4. That gives me x to the 2 minus negative 4. So I'm subtracting indices because it's division. And then y to the power of minus 3 minus 7. That gives us x to the power 2 plus 4, which is 6, y to the power of negative 10. But we want to express this without negative indices, so we say it's x to the 6 divided by y to the 10, because y to the negative 10 is simply 1 over y to the 10. But this is rather lengthy, and you might make a mistake with so many negatives. What you can do instead is rearrange, and everything that has a negative index, move it up or down from the numerator to the denominator or vice versa, and change the sign of the index. And this becomes x squared. We keep it in its place because the index is positive. Y to the negative 3, we don't want that. We want y cubed in the denominator. X to the negative 4, we don't want that. It's in the negative index, so we take it up. It becomes x to the 4. And y to the 7 remains in its place because the index is positive. And that allows us to give the answer simply as x to the 6 divided by y to the 10. Another application of the rules of indices is that we can simplify some numbers. For example, how can we simplify 16 to the power 3 over 2? Well, according to the rule, this is exactly the same as the square root of 16 cubed, or it's the same as the square root of 16 all cubed. But this doesn't really mean much. Sometimes, especially if the number is suitable, you can express it in index form. So 16 is simply 2 to the power 4. And that's raised to the power 3 over 2. And using the rules of indices, the power here becomes 2 to the power 4 times 3 over 2. And this is something that you can do in your head, of course. And this equals 2 to the 6. So this is a much easier way to calculate values. Consider this, for example. 4 to the power 2x times 2 to the x divided by 8 to the 5 minus x. The problem here is that the bases are different, so we cannot apply the rules of indices directly. However, if you look at the bases that are 2, 4, and 8, well, they can all be expressed as powers of 2. So 4 is 2 squared to the power 2x. And the 2 is simply 2, and here is the power x, divided by 8 is 2 cubed to the power of 5 minus x. Note the brackets. And applying the rules of indices, this gives us 2 to the 4x times 2 to the x divided by 2 to the 15 minus 3x. And those of you who can avoid this step and move directly from here to here are welcome to do so. Now, again, we apply the rules of indices. Those two indices are multiplied, so we add them and we subtract this index. So, if we take a shortcut, it's 2 to the 5x minus 15 plus 3x. Keep in mind, you're subtracting the whole thing, so it's as if there is a minus and there's a bracket. And this gives you 2 to the power 8x minus 15. Let's look at another example. 6 to the 5 times 3 to the negative 2 divided by 2 cubed. Here the bases are different and they cannot be expressed in the same way as in the previous example. But we notice that 6 to the 5 is basically 3 times 2 all to the power 5. And this helps us simplify things. So 6 is 3 times 2 to the power 5 times 3 to the negative 2 divided by 2 cubed. And this equals 3 to the 5 times 2 to the 5, because the power is distributed over indices, over multiplication I mean, times 3 to the negative 2 divided by 2 cubed. And immediately we can write the answer as 3 cubed, 5 times 2 is the 3, and times 2 to the power 5 minus 3 is 2. And if you want to calculate that, that's 4 times 27. Sometimes we meet fractions such as 3 over 5 to the power of negative 2. And we want to express this without negative indices and without brackets. So what we can do is simply distribute the power over division. So it's 3 to the negative 2 divided by 5 to the negative 2. And we don't want negative indices, so this becomes 5 squared divided by 3 squared. And if we think about this a little bit, this is the result of 5 over 3 to the power 2. Again, we have gone back to brackets, but if you notice that what we have done as a result from the beginning to the end is simply we changed the sign of the index and we have taken the reciprocal of what's inside. So we don't need this lengthy process again. What we can do, for example, is, let's say we have 5 over 7 to the negative 3. It is simply 7 over 5 to the power 3. And finally, sometimes we meet index equations. For example, 9 to the power 2x is equal to 27 to the power 5 minus 2x. And since this is an equation, then we want to solve it. That means find the value of x that satisfies this equation. In this case, the 9 and the 27 can be written both as powers of 3. So this is 3 squared to the power 2x, and this is 3 cubed to the power 5 minus 2x. And this can be written as simplified using the rules of indices as 3 to the 4x is equal to 3 to the 15 minus 6x. And again, if you are happy going from here to here, please go ahead. If you're confident, then that's okay. Now, the idea to notice is that you have 3 to the power of something equals 3 to the power of something else. The bases are identical. There is an equality sign, therefore the indices must be equal. So this becomes 4x equals 15 minus 6x. And if we continue the solution, you will find that 10x equals 15, and therefore x equals 1.5. Now, if you want to check your answer, then substitute the 1.5 into the original equation, and this gives you 9 cubed equals to, or let's check if it's equal to 27. 5 minus 2 times 1.5 is 5 minus 3, and that's squared. And you can ask, is 9 cubed equal to 27 squared? Well, we can check. 9 to the power 3 is 729, and 27 squared is 729, and that's correct. So this seems to be correct. Or, if you don't want to use the calculator, you can think of the 9 and the 27 again and put them in as powers of 3. So this is 3 squared to the power of 3, and this is 3 cubed to the power of 2, and obviously this is 3 to the 6 and this is 3 to the 6, so they are both equal. Again, I encourage you to write your comments, your questions, and your reflections. And that's it for today.